Question number 3 on the homework says, a solid lies between planes perpendicular to the x-axis at 0 to 4. The cross sections are squares, and the diagonals run between these two curves. So first step is we always want to draw a picture. So our picture would look like this. We're going out to 4. And it tells us then that the length between those curves at any given point is going to be the diagonal of a square. Okay, so it's going to come up from that figure to a point at any given place. That's going to be our diagonals between those two curves. Okay? Same thing over here. So first step is draw a picture of the solid. Second step, draw a picture of our cross section, which is a square, but we know about the diagonal here. Area of a square is side squared. We know about the diagonal in this problem. The diagonal is going to have a length of 2 square roots of x, because it goes from the negative square root of x up to the positive square root of x. So the diagonal length is going to be 2 square roots of x. So we need to work our way back to a side of this thing. If I have a square and I'm thinking about the diagonal, it's going to go right through the middle and give us a 45, 45, 90 triangle. So to work from the diagonal back to a leg of the 45, 45, 90, what do I do?
Divide by the square root of 2.
Divide by the square root of 2. So that's how long a side of the square is going to be. So 45, 45, 90 is 1 square root of 2. So if I want to work my way back, I have to divide by that square root of 2.
Which is just the square root of 2.
We can clean up that fraction if we want, but I'm just not going to worry about it right now because in my area formula then I'm going to have to square that. So I'll just worry about it after I square it. So then when you square something that has both a coefficient and a variable part, you have to make sure you square the whole thing. So I'm going to square and I get 4 over 2x, or just 2x is my area function. Often the problems that start looking disgusting are actually the ones that end up being really pretty straightforward in the end after some cleaning. If they start looking really clean, often they're going to end up getting messy as we go. To find volume, we integrate area, and we're told that this goes from 0 to 4. We get x squared. When we integrate, so we get 16 as our volume. Number 7 says the base of a solid is given between this curve on the interval of 0 to pi and it tells us that the cross sections are in part A equilateral triangles with that shape as their base. So for part A, we're going to do equilateral triangles there. And it actually gives us a picture of that in the book to kind of look at as well. So first step, draw your solid. Second step, draw a cross section. A cross section is going to be an equilateral triangle. One side of that equilateral triangle is going to be given by the function. We need area. Area of a triangle is 1/2 base times height. So our base is going to be 2 square roots of sine x. Our height, we don't know. If this is an equilateral triangle, each of the angles were 60. So when we drop that middle, we end up with some 30, 60, 90s. So that bottom's going to split equally, and each half of the bottom then will be a square root of sine x. in the 30, 60, 90 to get from the base side of the 30 to the long leg of the square root of 3, what is our pattern?
Square root of 3.
Square root of 3. So this ends up being square root of 3, square root of sine x.
Oh, that's.
And so that is our height.
Could we also figure it out because it's an equilateral triangle, all the sides are the same, so we know that the hypotenuse is 2 square root of sine of x. We can take that, square it, and divide it by the square root of sine of x. Sine of x.
You could know that the hypotenuse would be double. So the hypotenuse would be like the 2 square root of sine x. And then you could do like a Pythagorean theorem on that half a little bit. Is that what you're saying?
That's what I was saying.
You could, yeah. I think it's faster to just know like the 1, 2 square root 3 pattern, but that would work. When I clean this up then, the half and the 2 go. So I end up with square root of 3 sine of x. We'll find the 2 square roots together, they'll cancel each other out as well. So that's my area function. Volume, then integrates area. I like to throw any constants outside so I just don't have to worry about them when integrating.
Oh, that's really nice. How did I miss that?
What is the integral of sine?
Negative cosine.
Negative cosine. What is the cosine of pi?
Negative 1.
And the cosine of 0.
1.
So we end up then with 2 square roots of 3. Part B did the same type of problem, but it's actually a whole lot nicer. Part B was a nicer problem because instead of working with equilateral triangles, we're working with squares. So then our area is side squared, which is just going to be our curve squared. So we get 4 sine squared. I guess this is one of those cases where it started out a lot nicer, but then integrating this is not pleasant. So just probably finite that. (28) is a revolution problem. 28 says the region in the first quadrant, bounded above by the line y is the square root of 2.
This is Schrader.
Yeah.
For B,
Oh, nope, I'm reading the wrong question. Go ahead.
No. For B on that last one?
Yep.
Couldn't you have just got rid of that half for the area formula because the base and the height still stayed the same? So, would it,
Would the height be the same? No.
it wouldn't?
No, because the height of the triangle is square root of 3 square root of sine x, and the height of the square would be the same as the base.
Okay,
So,
I just assumed it did.
no, the height would be different. Okay, so 28 is reading the wrong question. In the first quadrant, bounded above by the line y is 2. And below by the curve 2 sine x, which would look like this. And we're going to take this portion here. And on the left by the y-axis, between 0 and pi halves, which would be there. And we're going to revolve this about the line of y equals 2. So I probably shouldn't have drawn this so close to the top because we're revolving it around up here to get our solid up that way.
Wait. So you're just flipping it around the line 2?
We're revolving it around the line of y equals 2. Instead of revolving it around an axis, it tells us to revolve it around that line.
So you're just flipping it upside down, right?
We're rotating it, so we're still getting a circular figure. We're still going to have a cone. It's just we're revolving it up instead of revolving it down. So this will be a cone figure. A solid cone. Any way that I cut it is going to look like a circle. A circle's area is pi r squared. So then we need to think about what the radius of any one of these circles is going to be. So in my drawing, this is a radius. It's a generic radius. It'd be different as I move along it, but I have to figure out what's a formula for that radius. Well, what's the biggest that the radius could be? 2. And we're going down to, the smallest would be at the point, we wouldn't really have a radius. Anywhere between there, how could I find out what that radius is?
Slope. 2
whatever the
sine
function
x.
is.
2x minus
Half of the function?
What's the question?
How can I find out what that radius is?
2 minus the function.
2 minus the function. So the function would give me this answer, and so I want to do the full height of 2 minus whatever the function height is. So our radius is going to be 2 minus the function. So that function was 2 sine x. So our radius is going to be 2 minus the function. Then to find volume, we integrate. We're going from 0 to pi halves, they said. This would likely be a finite problem. I would bet if you check your answer solution, they didn't. They probably squared this out and then used some trig identities to make some substitutions somewhere or something like that. This would be a finite problem. Being able to do trig substitutions with identities is not really something that you would be expected to do. So just being able to set it up and then being able to finite that would be what we would be concerned with here. $29. The region enclosed by x equals square root of 5y squared, x equals 0, y equals -1, and y equals 1. We're going to revolve around the y-axis. Okay, so to get an idea of what this looks like, we could solve for y and graph it on our calculator. It's going to end up being a sideways parabola. Then we're bounding that by x equals 0. Y equals -1 and 1 in this curve. So that's the shape we have. And we're going to revolve that around our y-axis so we get like an hourglass. Since as I draw that revolution, my circles are according to the y-axis, I'm going to want to work this problem with y's in it. Okay? That's fine and convenient because that's the way the equation was given. But if the equation was given the other way, I would want to get it so that it has y's in it while I'm working it, since those circles are stacking up the y-axis instead of most of our pictures, they've been stacking kind of over on the x-axis. So since they're stacking up on the y-axis, I want y's in the problem. So we are going to have a circle. Area is pi r squared. And for any given random circle, what is the radius? The function.
The function.
So we're going to have pi function squared.
It's not the x. It is the x value, right?
Hmm?
It's the x
The
value,
x value.
right? It's the radius, not the y value. That's what we're doing.
Because
Okay, so
I want y's in the problem.
Yeah, okay, that makes sense. I don't know why I'm confused. That makes total sense.
I'm gonna go, I always put pi on the outside, you don't have to. I also, when I square this, I'm gonna have that square root of 5 squared, that's just gonna become a 5. I'm gonna put that on the outside, you don't have to. I just like to put all my constants on the outside so I don't have to deal with them. And then y squared is gonna become y to the 4th. And we want y values as our limits on this thing since there's y's in the problem. So we're gonna go from -1 to 1. This problem we would integrate by hand. When I raise the power, I get 5. Divide by that power, and that works out really nicely. So then I plug in upper
So it's 2.
minus
Yeah, it's 2.
lower.
No, it's pi. Oh,
And so I end up getting 2 pi.
So volume is always the integral of area?
Volume is always the integral of area. Of our cross-sectional area. $33. 33 region in the first quadrant, bounded above by the parabola y equals x squared, below by the x-axis, and on the right by the line y equals 2. And we are revolving this around the y-axis. No, that's x equals 2. Bounded on the right by the line x equals 2.
Oh.
Alright, so since that circle that I drew is stacking up the y-axis, I'm going to want to work this problem with y's in it. Okay? Or I would want to do this problem by shells. Okay? If I solve this problem getting the x alone, I'm going to end up with positive and negative square root of y. Because I'm only working up in the first quadrant, I can just deal with the positive square root of y. So it's actually not too bad to just kind of solve it out this way. If I had some of it that was showing up in a different quadrant, then I would need to consider that plus and minus, and I would definitely want to go with shells on it. That method that we talked about yesterday where it's like the tree rings. On this one, I'm just going to go ahead and solve it for the x and use the square root. So any of those circles is actually going to be a washer. So in a washer, our area is pi big radius squared minus pi little radius squared. The full area minus the area that's missing. So what is our big radius? The big radius is always 2.
2.
Because it goes from the center of a revolution out to the outside of the figure, and that outside of the figure isn't changing. It's always that line of 2. So our big radius is always 2. And what is our little radius?
The function.
The function,
Square root of y.
which we're using as the square root of y.
So nice.
So then volume is the integral of that. I have y's in the problem, so I need y's as my limit. So what limits do I want for y? 0,
2.
2.
So there's supposed to be a pi out front.
4.
Yes, thank you. 4. If x is 2, y would be 4.
4x minus 1/2.
So I get 4y minus a half y squared. The pi out front. So then I get 16 minus 8. Plug in zeros and I get zeros.
My tests.
So about 8 pi. These problems can often be intimidating at the beginning because the functions look so gross, but they really have to make the functions gross so that once we square it in the area formula, then it's actually something nice to integrate. If they made the beginning function nice and neat, then once we square it, then it's a pain to integrate. So just kind of keep that in mind, like they're going to look intimidating at the beginning, but once you get it into the area formula, usually things clean up nicely, and if they don't clean up nicely, then it would be a finin. So, yeah.
How did you get, when you had the area formula of pi, big R squared minus little r squared,
Yep.
why did you put negative square root of y squared?
So the big R is the outside radius, which is always 2. And then minus the little radius is always going to be the curve. And the curve we're working with is x equals the square root of y. So our little r is the square root of y, and then our area says to square that.
And then this was using a calculator, right?
No. This would be non-calculator.
Oh yeah, okay, yeah, you can.
39 asked you to specifically use shells. For 39, says use the cylindrical shell method to find the volume of the region revolved by generating around the y-axis. So it gave us y equals x, y is negative x over 2, and x equals 2. So that region looks like y is x, negative x over 2, and x equals 2. So we want to take that triangle and revolve it around the y-axis.
Sweet.
Yeah, you're gonna want to use shells here.
So if we can do this problem without shells. And so this is the kind of problem that the AP test could ask where shells may be a little bit easier, but it's possible to do without. I don't actually even know if shells is actually the easier way to do this one. So I'm going to show you how to do this one with shells or without. If we do this problem with shells, we're thinking of cutting out a very thin tree ring here, and then slicing down the side of that and unrolling that to be a sheet of paper. So we're taking a whole lot of sheets of paper and rolling them up to make this figure. The length is going to be the circumference, which is going to be 2 pi r. So in our picture then, if this is our any given circle, or we have some smaller circle, because it doesn't have to be the full circle, we're cutting all of those shells starting all the way from the center and working our way out. In general, what is the radius?
X.
X. So it goes from the center of the revolution out to wherever the edge of that circle is. So our radius is X. What will the height of those shells be?
No function.
Can you explain one more time why r is equal to x?
So I've got lots of different rings drawn out here,
Yeah.
and they all have a different radius.
Yes.
But that radius goes from our y-axis out to some x value.
Okay.
And it could be any x value as we move our way out.
And then take
Okay.
back my statement, the height is the functions added together.
So when I only drew like a circle here, but really we're doing a shell. So we've got kind of the top and the bottom, and this is really what we're cutting out is a cylinder. Okay? So what is the height of that cylinder?
The two functions added together.
So function times 2.
Does it?
There's
No.
two different functions.
Oh.
So we can't use symmetry. The top function is y equals x. The bottom function is negative x over 2.
So 2 and -1.
Added together, right? Is it not added together?
Not subtracted. It's going to end up as addition because that one function is negative, but we actually need to subtract them
3.
to get the difference.
Okay.
So it's going to be the top function minus the bottom function will give us the height. So it ends up as added because that bottom function is negative, but really what we're doing is the top function minus the bottom function to
Okay,
get those two individual heights added together.
yeah, I guess that's what I was.
So that ends up being just
You don't get,
3.
you get
3x over 2.
Yes. I think I had that.
So then
Shut up.
Base
area
times
is
height.
base times height. And I can reduce that down and I get 3 pi x squared, which we're going to integrate. From what to what? What are possible x values for this problem?
0 to 2.
0 to 2. So, because really the shape was only this part over here, that other part's just kind of like the ghost that's created by the revolution. So the shape itself goes from 0 to 2, not negative 2 to 2. So then integrate that, and I get 1/3 x cubed. I have the 3 pi out front. The 3's cancel. I end up with 8 pi. We could do this problem without shells. So I'm going to show how to do that also. So to do this problem without shells, I would think of stacking up washers, because they're going to have empty middles, along my y-axis. So if I'm working along my y-axis, that means that I would want y's in my problem. So y equals x, that's not an issue. But for the other one, I want to get x alone. So negative 2y is equal to x. And then I'm going to have washers. What is the big radius?
2.
2.
Yes.
Because it's always going to have to go out to the edge of that shape. So our big radius is 2. And what's our little radius? Okay, the function, but there's actually two functions. So that might be where shells is maybe a little bit easier of a way to do this. Because on the bottom half of this, we're going out to a function. But on the top one, we're going out to a different function. So we're going to have to split our integral. So our big radius at the top is going to be, or our little radius at the top is going to be y. Our little radius at the bottom, I don't really want to do division, just kind of separating the two ideas, is negative 2y. So then we're going to have to do two separate integrals. For the top, I would do 4 minus y squared. And what would my limits be for that top one?
0 to 4.
0 to 2?
Right.
Yeah, because it's y equals x. And we're going out to 2. And then I would need to add that to,
Negative 2.
for the bottom one, I still have 4 as my big radius, but my little radius is now going to be,
2y squared.
when I square it, I'm going to get a positive, nope, negative 4y squared.
Oh, wait. Okay.
And then, what are my limits of integration going to be there?
Negative 1, 0.
Negative 1 to 0.
1, negative 1, 0.
Because this line is at x equals 2. So if x equals 2, then y would equal negative 1 for that bottom function.
Okay.
So shells is maybe a little bit easier way to do this because you get to keep it all together as one integral. But shells can also be pretty baffling to work with. So this is possible to do without. So this is the kind of question that they say is fair for AP. Having to do shells will never be necessary on the AP exam. But sometimes it might be easier. And that's kind of where they leave us as being an AP teacher with a choice. There's a lot of things they say, you have to teach this, you have to teach this, you have to teach this, you don't have to teach this. Shells, they say, you might want to, but you don't have to. Because you'll never need it, but sometimes it might be the easier way. Okay? All right.
42. Or 42 and 44 the same.
42 and 44 are both also shells problems that are the same kind of thing, so that's why I just didn't look at them. Like, I think we're not going to do them. Yeah. We're not going to do 42 and 44, so that leaves us with an exploration.
It's like 5 minutes.
Yeah, except for I looked at it and was like, I don't remember the years, this was like something we learned a while ago.
Okay. Did you get all those notes? Did you get all the notes?
You're gonna waste a lot of your time on
Yeah, we're gonna waste of semester.
Right now?
Yes.
This chapter is kind of a combination of AB and BC stuff. Area and volume are AB, but what we're going to do right now is BC. So chapter 7 is kind of a mix. 1 through 5 is all AB. 6 and 7 are kind of a mix. 8 to 10 are all BC.
So if we decide to like
There's
to just kind of like 8 through 10 is optional.
I'm still going to suggest that everybody take the BC exam just because you get your AB subscore.
Okay.
But just kind of know that, like, if 8 to 10 are more rough for you, but the beginning of the year stuff went better, that you'll still have your AB subscore to fall back on.
Okay.
But I would still suggest doing BC just at the possibility of, hey, if you can, wing it and still get a passing score, then you get 2 semesters instead of 1 semester.
I don't know if that's
Do they
risky.
specify on the exam which ones are A, B, and BC?
No.
Oh my god, I'm like,
You just have to remember.
Well, I mean, do your best on every question and they'll take care of it. So, but yeah, otherwise you would have to remember if you really wanted to know if it's going to be an AB or BC. And even then, every question on the BC that's on an AB topic doesn't actually figure into your AB subscore. It's only the questions that are exactly the same as questions on the AB exam. Because some of the questions exactly match, and those ones they'll score. And other ones that are still maybe an AB topic, they won't score. All right.
Oh, this is huge.
Let's look at
chapter 7 was so easy.
exploration 53.
That's the Navy SEALs, dude.
That's the Marines.
No, that's the few outbreak.
These are strong.
And there's Army Strong. That's the Army. Learn and do stuff.
All right,
Should just roll.
ready?
Yep. Yep.
In exploration 53, we're going to look at something called the length of a curve. When we're talking about the length of a curve, I'm thinking if I would take a piece of string and lay it along the curve and then straighten out the string, how long is that string? Okay, that's the idea that we're talking about when we talk about arc length. So we're beginning with an example where we're going to look at the graph of x squared from x is -1 to x is 2. It says draw the line segments connecting consecutively the points in the graph where x is -1, 0, 1, and 2. Okay, so what we're going to do is connect with a straight line, -1 to 0, 0 to 1, and 1 to 2. We can find those by looking at some right triangles. So on the left, that triangle would have sides of 1, 1, and hypotenuse of
Square root of 2.
square root of 2. On the right, that first one is also going to be a 1, 1, square root of 2. And the second one is going to have a base of 1, a height of 3, and a hypotenuse then
No.
2.
of
Square root of 2.
Pythagorean theorem,
Square root of 10.
square root of 10. So if I add up then square root of 2 plus square root of 2 plus square root of 10, that will give me an approximation of the length of that curve. Is it going to be an over or under approximation?
Under.
Over.
There's a little bit of a difference of opinion there.
It's gonna be
Under. Listen.
That would be
If you buy
under.
a belt that's straight, way under. You're gonna be way under. If you buy it with slop, you're gonna be.
So when I work that out as a decimal, I get 5.99.
I think it's over.
That is going to be an under approximation because connecting 2 points with a straight line is a shorter distance than connecting them with a curve. So the actual length of the curve is going to be more than 6. Okay?
Yeah.
This is actually a decent approximation. I mean, we only cut it into 3 sections, and those straight lines are really following the curve pretty closely. We could do better if we cut it into more sections. So if instead I connected all the halves together, that would be an even better approximation. It would be annoying to do though. So we're not going to.
Alright.
Um,
Teacher ever.
So we would need to calculate then each of those little right triangles. That's a whole lot of Pythagorean theorems with 0.5s and squaring them, and it's just not something I feel like doing. What we're going to do is come up with a formula in general that will help us then determine how we could find the exact length. So I'm going to take this little segment here and say I could make a right triangle out of that. First we counted by ones, then I said we could do better by 0.5, so we could do even better by a quarters or by 0.1 or by 0.01. So in general what we want to do is make this as small as possible, and we're going to call that dx. Then when we change x by some amount, y is going to change by some amount as well. And we can find our hypotenuse by the Pythagorean theorem.
Square root of dx.
Square root of bad.
And this is our formula for arc length. So length of a curve is equal to, okay, dx is the derivative of x. If we're working with x's in our problem, then what's the derivative of x?
1.
1. And then dy is going to be the derivative of our function. And we're going to square that. That would give me the length of one little segment. If I want to add up a lot of them, how do we add? A lot of things.
Sigma.
These, yeah, those signs.
Sigma, I would need to know them all.
H's.
Calculus, how do I add up a whole lot of rectangles to find area?
Integral.
Or a whole lot of circles to find volume?
Integral.
We integrate.
We just put a lot of pluses.
So in this problem, if my equation is x squared,
Yes.
then
Plus,
dy
plus.
dx is equal to 2x. And I'm going to integrate the square root of 1 plus 2x squared from, in this problem, -1 to 2. This is probably a finenter.
Yeah.
You can do it, it's just not nice.
Or I don't think you can do it. not this one.
Do you question my abilities?
And I get 6.126. So our first approximation was really pretty good for only having drawn a few triangles. But this is how we find the exact. And that's what the next section of the notes is about. So on Monday, we will talk about 7.4. Your only homework for Monday is your journal.